Hello. So here's my second development video. Just setting everything up. So I have a proper webcam now. Recording in OBS, and I wrote something down so it's maybe a bit more structured. So in the last video I went through a bit of my background and how I ended up being a developer. And again, I haven't practiced anything. I just turned the camera on and let's see how this goes. So in the last video I went through a bit of my background and what sort of things I've done, and I thought I'd sort of dive deeper into various things. So I guess I'll talk about my early influences. So as I said, I've always loved playing games, and I've always sort of considered game developers as some sort of geniuses and heroes, because they can create something that so many people enjoy, and especially I enjoyed them. So the thought of being able to make something that is so much fun was somehow really magical. And then during my studies in the University of Applied Sciences, so not the theoretical university but the practical one, we had the basic, we started learning programming with the basics, like learning syntax in C and C++ and C#. And we went through the normal stuff like for loops, if then if else statements and stuff like that. Of course, very important things that you need to use, but I distinctly remember that the exercises that we had to go through in the courses were really boring and didn't really capture me. Stuff like, here's a list of politicians and their yearly salaries, put them in alphabetical order in one list, and then in another list where their salaries are in an ascending order and stuff like this. Of course, important skills to be able to control lists and manage them and stuff like that, but it was really boring and sort of soul crushing in a way, because you were forced to do something that you in a way know that it's important and you have to learn it if you want to be a software developer, but somehow it just doesn't capture your attention. There was there was one course where you had to make a poker game, and that I remember was at least interesting because there was some sort of logic and a gameplay structure to it that you had to get right, and I remember that was interesting. And then another course where we had to experiment with sorting algorithms, like bubble sort, and I don't even remember the other ones. There's bubble sort and the others, and then you would sort of test those against each other and see which one is the fastest. And that was really interesting because getting a grasp on different algorithms like that was very interesting. Of course, thinking back, I've never used that information, but it was interesting and sort of somehow captured something in me that made me sort of think about programming in a, I can't really explain it other than that it was really interesting and sort of captured my attention. And then we had different courses where, when I had already started to learn Unity, and I had made the prototypes for Quake mechanics and stuff, and then we had software development course. So I of course then created or took my game and sort of worked more on that and presented that as my course project. And I ended up making sort of physics-based grappling hook mechanics, where you have these boxes on top of pillars, and you have to there are red boxes that are really light, so you can shoot them with your bullets and they fall down, and then you have green boxes that are really heavy, so the bullets don't knock them down, so you have to jump and then grab the box with a string, and you swing around so your weight pulls the box down from the pillar and they fall down. And that was really fun. And the grappling hook mechanics was really challenging to get to feel right, but I ended up getting it to feel pretty good. The only issue was that the hook was actually, or the string connecting you to the point of contact was actually a rigid pole, so that you could actually, if you shoot it straight down to a surface, you could stand on top of it. So it was actually just a rigid stick. So in order to make it work smoothly, you had to use it so that when you were traveling next to a surface, you had to shoot it at a 90-degree angle or more away from the wall, because if you were traveling next to a wall and then you shot it at an angle in front of you, you would collide with the stick, so you would lose momentum. So obviously it wasn't ideal, but it was still a lot of fun if you used it the right way. And so during my studies I learned a lot of programming basics and syntax, and sort of got a really good general understanding of programming and general software development practices. But like I said, the topics and the projects that I had to do were not very they didn't really interest me in a deep level. Okay, there was one project where me and my two classmates, it was like a, what do you call it, integrated systems, where we had a Raspberry Pi, and then we got an ultrasound detector, which basically sent ultrasound and then it bounces back to it, so it detected the distance of travel. And we basically made an ultrasound detection device or the plan was to have a device for a blind person who could point the device at various objects, and he would detect through vibration how far the object was. So he could have like an ultrasound blind navigation device, or whatever you want to call that. And that was a really interesting thing, because we programmed it in Python, and we had to find the documentation of the ultrasound device and calculate the distance based on how long it took for the signal to come back and stuff like that. It was really interesting. Of course, it wasn't really functional, because ultrasound bounces from different surfaces in a different way. So for example, if the surface is really flat and reflective, you don't really even get any signal back, or even though you're pointing it to the surface, which is say 1 meter away, because the surface scatters the signal, it comes back from way too far away, so you get the result of maybe 8 meters, even though the surface is 1 meter away. So it was obviously not a proper a useful product, but the project was very educational and interesting. So so I did learn C, C++, C#, some JavaScript and Java and stuff like that, but I only really enjoyed C, or well, in general the basics are of course the same in all languages, but then C# and was the thing that sort of somehow made the most sense to me. And then also when I found out that Unity uses C#, I obviously focused on that. And like I said, I paid the freelancer to make the prototype of my flying game in Unreal, and so I did sort of dabble in Unreal a little bit, try and figure out if I can use it. But the issue was that I couldn't find a lot of information or tutorials or stuff like that on Unreal, especially the programming part, and so I didn't really get to any sort of speed using it. But then when I tried Unity, there was so many videos about it. Like, it had been used for quite a few years already, so the amount of tutorials on all kinds of different subjects was crazy high. So it was much easier to get started in Unity because there was so much tutorials on it, and that's how I got into it. And like I said in the previous video, I spent a lot of time learning the ropes and getting more comfortable with it. And so the challenges, different challenges and issues were basically for a long time I struggled with really understanding input and sort of how to make the controls do exactly like I want them to do, like row mouse input, or having the button control the force in exactly the way that I want. And this I've never been really good in math. I knew that I need math, so I when we had the course for vectors and matrices, I knew that it's important, so I really focused, and I did pass it with a good grade. But because I'm not very proficient in math, I don't have like a really deep understanding of it. But because I used vector math, like vectors and dot products and cross products and stuff like that in Unity a lot, I sort of started to get an intuitive understanding of them. But the thing then, when you try to create an algorithm that works well and feels good to play, for like pressing a button, how the character accelerates, and how do you prevent the acceleration to go infinite, and sort of how do you decide where the maximum speed is and how you reach it so that it feels smooth, and all kinds of small details like that. There was a lot of experimentation with just different simple math algorithms, like 1 over the distance or 1 over the current speed, and sort of trying to get the, so for example I came up with a, what did I call it, like a dynamic max speed for the character, which was basically that in Unity you have the physics object, the rigid body, and you can control the drag, basically the air drag that it gets when it keeps going forward. There's a force that acts against it. So what I did was that the faster you go, the drag goes higher, which is of course how physics works on Earth. So the faster you go, you multiply the drag value by your current velocity times a certain multiplier, and then you tweak that multiplier to make it so that if you keep accelerating infinitely, you reach a point where the force against you is too much, so you basically reach a max speed. But this algorithm makes it feel really smooth. You can't tell it becomes really gradual and feels really natural. So that was one thing that I found really nice. And for example, the Quake movement mechanics, basically what they call air strafing or air control, where you're moving forward. Let's say you're moving directly towards the camera and you want to maintain your speed, and turn your velocity. So what you do is you don't press forward, you press strafe to the left, which initially doesn't do anything. When you're moving that direction and you press strafe in that direction, nothing happens. But then when you start to rotate while keeping the strafe key pressed, then you start to alter your direction. And that I remember that involved using dot products, because dot product is basically if you have a vector in that direction, and if you take another vector which is pointing in the same direction, I think that then the dot product is 1, and if it's 90 degrees it's 0, and when it's against it it's -1. So when it's to the side it's 0, and then when you start to rotate a little bit, so it's pointing a bit more than 90 degrees, then it becomes -1, and you can use that small amount of -1 or -0.001 or whatever. So that's the thing that then starts to turn your momentum. All kinds of small details like that, which it obviously took a long time to sort of get the grasp on that, and I think I've forgotten more than I currently remember, obviously. But as they say, it's more important to learn something and then forget than never learn it. So I did learn it at some point. So that was really interesting. And then I remember back in when I made the Quake prototype. So I did, like I said in the earlier video, I made the Quake mechanics prototype once with using the Quake source code, which was using how would you say, it doesn't use physics, but the player position is in XYZ, and then it just changed the position every frame, compared to using a physics engine where you have the physics object and you apply forces to it, and then the physics engine does the teleporting of the object. So basically they do the same thing, but in one you explicitly tell the game where you want the object to move, and with the physics engine you just give the forces and it moves it. So in a way it's easier to use the physics engine because you don't have to do the math, you just give the commands. But so I did do the proper Quake style as well, but I remember in the Quake source code the ramp mechanics were not there. So in Quake 1 at least, if you're moving up a ramp and you press jump, you jump higher than if you were moving on a flat surface, because your vertical momentum is added to your jump speed, and that for some reason didn't work right away, so I had to make that myself. And I remember I did get it to work, and also got it to work so that when you fall down to a ramp while holding jump, you get the sort of bounce effect of gaining more horizontal speed. So you jump a bit lower, but some of the speed is translated to horizontal movement. And then of course I did that with the physics engine, which was much easier. You didn't have to do anything, you just applied in Unity you have the physics material. So basically you apply a physics material to your character, and you can determine the bounciness of the material. So you just have a surface and you land on it and you get the bounce effect. And then I also made it so that the jump direction of my physics-based Quake controller was that you jump up in relation to your view. So if you're watching directly forward and you press jump, you jump straight up. But if you view 45 degrees down and press jump, you jump 45 degrees up. So that way you can, so I made it so that you can actually do wall jumps. You jump at a wall and then you look a bit up as you're connecting to the wall and jump, so you jump a bit away from the wall. I remember I got that idea from one of the CPMA guys. No, I don't remember his name. I think Ixi maybe? Something like that. Shout out to Ixi. if I remember correctly. And so that was interesting. And then also my physics-based Quake character was actually the object that the player actually was a sphere, and the way I moved the character was on the ground was that I apply rotation. So you roll, but your camera stays of course on top and aligned properly, but the character rolls. So I apply rotational movement, but also some add force laterally, which means that if I have a wall and I'm moving at a high speed towards the wall, and the sphere is rotating as it impacts the wall, it bounces up slightly because of friction and the rotation. So that was really interesting because you could do you sort of wind up your rotation speed like Sonic the Hedgehog, and when you hit the surface you bounce higher up, and so that was really cool. And so the grappling hook mechanics, for example, I made it so that it was interesting. I couldn't get it to feel good at first, but then what I did was when you point at a surface and you shoot the grappling hook towards the point. So this point, I called it the anchor. When the anchor hit the object, the anchor was attached to the player, and then pressing the movement keys actually applied rotational forces to the anchor. So basically the anchor became like a stick that was holding the player. So when I press forward, it would swing the player down. So I hit an object on the wall, and then I pressed forward, which applied forces to the anchor, and it swung the player like that. And this made it so that I could hit it on a stick, horizontal stick, and I just keep pressing forward, and I would start to rotate faster and faster around the stick, and it was really fun. And what else? Also, that made it so that when I was standing on top of one of those boxes that you had to pull down. Oh, now I remember. That system made it so that you can climb on walls. So you have a wall and you're standing next to it and you shoot the grappling hook there, and then I push back, it would lift me like this, and then I shoot it again here and press back, so I can sort of climb like that. And that was actually really cool. And you could also then sort of fly with the boxes, because there was the box like that, and you attach yourself to it, and then you press back, so it swings you over the box and just keeps swinging you, so you sort of start to fly with the box. There was fun bugs like that. And so yeah, I did a lot of those. I also added in Quake 3, or initially in Quake 2, so in Quake 1, in Quake 1 you had the air control, so if you wanted to go faster, you did it so that you press strafe and then you wiggle like this. So you're always straight to the direction you turn. But then in Quake 2, you accelerate by pressing forward and strafe and slowly turning. So you sort of do smoother curves and you accelerate faster, and that was also the way to accelerate in Quake 3. So what I did, I added that system, but then you also get a bit of speed from the wind up of the sphere rotating. So every time you land, you get a small speed boost. And also depending on how much forward, how much down you look, the jump direction is also a bit forward. And then I had another project which I did for an eye doctor. So there was a doctor doing a thesis on using different applications for testing people's eyesight. And so I made some prototypes for things like you have, I think it's called anaglyphic 3D, where you have glasses that the one lens is red and the other is cyan, I think, red and blue sort of. And then I had a red dot and a blue circle on the screen, and the red dot was in the middle, and then you control the blue circle with your cursor and you try to get it in the middle. And then when you see that they are on top of each other, you then remove the glasses, and if they're off, that sort of that indicates your, I forget what it's called, sort of the issue with your eyes looking in the same direction. And then I had another thing where I used the same anaglyphic 3D, and I had a 3D scene where there were 4 spheres, and then one of the spheres was either further or closer than the others, and you had to be able to tell which one is the one apart from the others. So you could test some depth perception, and then I had the basic precision or acuity thing where you had the letter E and the E was on the center of the screen, and you would look at it, and then you use the arrow keys to hit which direction it's pointing, and every time you hit it correctly it becomes smaller and smaller and smaller, and it sort of gives you points on how far you can go without making a mistake. And then once you start to make mistakes, that's sort of the level where you can't progress anymore. And was there another one? I think those were the things that I made for the eye doctor. It was really interesting. And in general, I had this idea to talk about my development philosophy in terms of game development or user interface or user experience side of things. So for example, one example of the concept of error minimization and or success optimization, basically meaning that, for example, in Quake, when you fire a rocket at the enemy, in Quake 1 it always worked so that if here's the enemy and you shoot the enemy with a rocket and it hits his toe, he's pushed up away from the explosion. If you hit the ground in front of the enemy, so it isn't a direct hit, it hits right in front of the enemy, he's bounced up. But then in Quake 3, the default vanilla Quake 3 arena, for some reason, the direct hit of a rocket would push the enemy in the same direction as the rocket was moving. So basically, if you fire a rocket from above a player and you hit him on the toe, he's pushed down. But if you hit 1 pixel in front of him, the explosion pushes him away from the explosion, so up. And in Quake, you always want to hit the rocket so that the player goes up in the air, because then they can't dodge, and it's much easier to hit an enemy who is on the ground compared to someone who is moving sideways like this, trying to dodge your attacks. So I pointed this out, that it makes much more sense to always make the rocket push away from the explosion point, because then you're actually, otherwise you're penalized by hitting the enemy directly. So that was an interesting concept, and I think they ended up changing that in CPMA to be more like in Quake 1. And then in general, I've always had this idea that that was an example of where the margin for success and or getting the effect that you want and the effect that you don't want, the line between them is technically the line between 2 pixels. And I think that sort of a design in general is a bad idea, because I think in general it should be a smooth spectrum of gradually getting worse the further you are from the optimal point of contact. So for example, if we jump to a different thing, for example, UI design, you have a button that you want to press. I'm jumping all over the place, but so I made this virtual reality application where you have a laser pointer and you click on spheres and they pop. And what I wanted to do is that, because in general in VR applications you just get the raw input from the controller, and because the controls are really accurate, they have a really good inertial measurement unit in them, and then also the visual system of tracking them. So they actually get all your micro movements. Like if you have slight jitter in your hand, you can tell from the laser pointer that it jiggles. So if you have a button you want to press, which is kind of small or far away, it might be actually difficult to hit it. Like for example, I had a friend who came over after a long night of drinking, and his hand was shaking like crazy. He wanted to play Beat Saber, but he missed the play button like 5 times in a row, and he got frustrated because he couldn't hit the play button. And I thought this, like, it's an extreme case of someone having a hand jitter, but some people just have jittery hands. So obviously you have to have a sort of an accessibility feature for someone who has a jittery hand. So I came up with a really simple algorithm where you basically, in general in Unity, you have the VR controller, and you just use the VR controller's location, and you shoot the line from that. But the thing is, what I did was that I used a separate object that was not attached to the controller, but it was a separate object, and I just used a script to tell it to follow the hand. And then for the rotation, I made it so that I compare the two vectors, so the forward vector of the controller and the forward vector of the line or the pointer. And then the speed of the rotation of the line is not only the movement of the controller, but it's controlled by the distance or the angle between the two. So at first, if your hand moves only a little bit, the angle between them is really tiny. So the line barely moves at all. But then the further you turn the controller, the larger the angle becomes, so the rotation becomes faster and faster. And if you fine-tune the values or the multipliers for that, you get it to feel so that you can very easily keep the line pointing exactly where you want it to, but it's still, if you want to do a quick movement, it follows you. So it's basically, I think, the way VR pointers should be made. Like, you don't want the hand jitters to be expressed in the VR pointer. Of course, it's a different thing if you want to make a VR gun simulator where you want your users' hand precision to actually matter. But in general, UI UX design, you don't want that. You want it to be easy to hit the button that you want to hit. And then another thing is that this is one of my pet peeves. It makes sense when you're using a mouse. I guess most people are used to the thing that you have a button and you can press down the mouse button on the button, but then you can sort of cancel by just moving the mouse away and letting go, not having the cursor on the button, and you didn't actually press it. But then if you have a VR pointer and you try to click on a button with the controller, it often happens so that when you pull the trigger, your hand moves away from the button, and then you didn't press it. And that often causes errors. So people unsuccessfully try to press a button. So I think in VR it makes sense that when a user pulls the trigger while they are pointing at a button, the button should activate. So that's another thing that I added to my pointer application. And so yeah, like I mentioned in the previous video, I gained a lot of confidence doing all those things. I didn't even mention everything, but there was a lot of various small projects that I made. Like most people, I didn't finish most projects or any, I think, but I learned a lot from them. I sort of considered them to be learning projects and just something fun for myself, like making the prototypes that I wanted to play. And I actually spent a lot of time playing my own prototypes. And but then once I graduated, some of my professors from the university suggested that I should apply, and then I got contacted by the boss of the R&D department, and I was hired. And I've learned so much working for the university. Like, actually, before I started to work there, I had a lot of social anxiety, and in general, speaking to people, especially to crowds of people, was terrifying to me. It was always really terrifying. Just going in front of the class and talking to students that I've been with for years, it was terrifying. And I was sort of thrown to the deep end right away, because part of my job was sort of demonstrating the VR equipment and the various projects to groups of people. Like, they were within the first year, I think we had roughly, I'll say, 30 to 50 groups of 10 to 30 people visiting the lab, and I had to speak Finnish and English back and forth. So I noticed that basically all my social anxiety went away, and that was actually one of the things that was really sort of weird, because whenever a new group was coming, I started to realize that, or I started to notice that I have no anxiety. I'm not stressing it. It was often either indifference or just frustration that I have to go through the whole thing again, and I can't work on the project. I have to spend time talking to people, and the thing is that often the differences between groups are really huge. Some people they don't say anything. They don't want to try the VR headset. They're afraid. They don't ask any questions. They just wait for you to say stuff, and then they leave. And that is often really frustrating, or sort of demoralizing in a way. But then some groups are really amazing. Like, they're excited to try, and they ask questions, and they have ideas. And so some of the times demonstrating to groups are really awesome, and I learned a lot. I made a lot of cool connections with companies, and often there were visitors from other universities in Finland, so that's also really cool. And I learned a lot about how industry, especially construction and automation, are sort of getting to grasp with how the new technologies can actually be beneficial, like actually save them money or make them work faster. For example, there's one company who make these really large multi-ton devices that control, say you have a huge, for example, you could have a car attached to the device, and you can rotate the car to be at a certain angle so that the welder can work on the object in a good ergonomic position, instead of having to bend over and reach a really difficult spot. So you can rotate and move the thing. And so we got that, and my colleague made that as a VR project that the company could then go to. Say there's an expo where they take one of their devices, which is like a multi-ton thing and costs thousands of euros to take there. So they can show that at the expo, and then they can show all their other devices with the headset. So that is actually something that companies now use. So then, of course, nothing beats the actual device, but you can then show all the other devices with the headset. And then there's, for example, a company who they build like what do you call them? Like garages and small buildings and storage buildings and sheds and stuff like that. So what they do is they have a smartphone app that you can open the camera and you can spawn the 3D object of the building at the location you want it, and then it's in 1:1 size and scale, so you can walk and look through your phone what it's going to look like, and you can actually walk inside the building and look out the window with your cell phone and see what view you're going to see when it's done. So something like this is really beneficial for marketing, for example. And then now there's talk about how it's useful to use stuff like this. For example, if you have a company who does let's say they build large machines, and then they send the machine as parts to the location where it needs to be built, and then the people who actually put the parts together, they haven't actually seen the device, what it's supposed to look like when it's ready. So if they only have a 2D picture of like the layout and how it's supposed to be put together, they might make mistakes. But if they have, say, a cell phone AR application where they can see it, or say they have a VR headset that has pass-through, so they can put the headset on and they can see the virtual version of the device, what it's supposed to look like when it's ready. So they have a visual representation of what they're building, so they can check that they don't make mistakes. So that's one of the directions that the technology is actually helping companies. And that's one. And then, for example, the Quest Pro is one that we've demonstrated where it has the pass-through. So, for example, you could have, it's maybe not yet there, but it's going to be there soon, that someone at a car mechanic shop or somewhere where you fix large things, I don't know what, so you could say next week you're going to be sent a thing that you need to fix, and you've never seen this device in your life. So you can have the headset on and you can get the virtual version of that object there, and then you check from the list in the VR application that, okay, I need to switch this, I need to take this part out and replace it. And you find the part in the VR object and you can check which things you have to take out first so that you can switch this part out. And you can sort of go through the process so you know what you're about to do when the actual thing arrives, and then you already know what to do and you work faster. Or for example, at a construction site, we actually had last year the what's it called, the Spot robot, Boston Dynamics Spot robot dog visited us and a university, and one construction company was doing a thing with it where they had a laser scanner on top of the Spot, and it would walk around on the construction site and make a 3D scan of it. And then the plan is that in the future, at the end of every day when the workers go home, you would make the 3D model of the construction site, and then, for example, the next day the inspector needs to come and check out something. So while he's maybe traveling to the site or the day before, he can go through the 3D model and check, okay, here's one issue I need to check out. So he doesn't have to go through the entire construction site himself. He can just directly go to the point where there's an issue and check it out. So for example, that way it actually saves a lot of time, and it's easier to do things because you have these digital models that you can really easily visualize and use. And then for example, you could use a headset where you go to a building and then you have the building's infrastructure layout within the device, so you can put the device on and then you can sort of see through the walls where the like air vents and all kinds of plumbing and stuff like that is. So if you want to do some construction, you can sort of see where everything is, so you know, like stuff like this is going to make construction and industry sort of much more efficient in a way.